Okay, for people joining this live stream, we are looking at functionality planned for 12.1, and this is in the Calculus and Algebra area. Great.
So,
by the way, I'm sorry, somebody needs to be on mute who isn't. Okay, go ahead.
Just to summarize, so we've been rolling out asymptotics as a gradually as a full third mode of computing to numeric, symbolic, and asymptotic.
So I gather, yes.
Okay. Now, the three new functions this time around, and their design augmentation or changes for the existing ones that we rolled out. So the three new ones.
I'm scared about one called just asymptotic. That's the first one on this list.
This is going to be, yeah. Wait, before we drill down, can I just?
Yeah. Okay. Yeah.
Okay. So the design changes is in the way that you give, we've looked ahead for multivariate versions, because for most cases we don't have multivariate versions of this, but we looked ahead, even if we can't implement right now what the design would be, so we're not sort of cornered, and so on. What can I say? There are improvements to the existing one, and there will continue to be improvements. So then let's just drill into the ones that are new.
Okay, but so hold on. Okay, so asymptotic product, I understand. That's okay. The one that I'm really...
So the big thing that will do, apart from a sort of expressions, is that it can deal with operators effectively. So if there is an unevaluated integrate Laplace transform, so we've elected not to design asymptotic Laplace transform, asymptotic inverse Laplace transform, asymptotic Fourier transform, asymptotic inverse Fourier transform.
So I don't understand why this thing, unlike series, which has x, 0, 5, right? Oh, that does that too.
Right. So actually, the point is there, the leading term is very important. In many cases, all you can hope for is the leading term. If it's advanced enough, hard enough, getting a leading term is challenging.
So are we going to support this syntax for series as well?
We have not changed the series at this point, but we could. In which case, what you need to do is the same thing as we've done here, is that there is an option that tells you how many terms. It's called asymptotic terms.
Well, I understand, but I think that series, the difference here with series, obviously, is with series, and I'm now confused, because if I do this, I'm very confused here. It's going to be the same, right? So the place where it isn't going to be the same, if I say, like e to the 1 over x or something, okay, and I do the same thing with series, e to the 1 over x. Okay, I'm totally confused. What's the difference? It's not just that one of them is a rewrite.
No, so actually asymptotic does make use of series in a refined way, and you'd start to see that for some expressions, particularly when there are branch cuts and
so let me see that.
And Stokes lines.
So where does it start to differ?
Because it can handle it. I think that the key use case is that you can have. We need an asymptotic inverse Laplace transform, and every other integral transform is summation transform.
Yes.
So where is that going to happen? Most of them.
So what about a series expansion for those things? The way series works right now, the thing gets evaluated and then it seriesifies it afterwards. Is asymptotic something that doesn't evaluate its arguments?
No, it does evaluate its arguments. So
if I put in here something like e to the x, I don't know, e to the x squared or something there,
then it would follow the evaluation order.
So in other words, what this just...
But if you had inactive of integrate, do inactive integrate. It should still work.
Hold on. So I get that. Okay, so if I say inactive integrate. Okay, now if I do the same thing, if I did that with series, e to the x squared, no, integrate. Okay, so let's just
that integrate just evaluates. So it's.
I know. It's not going to make a difference. Okay, so then I say x0, 4 or something. Fine, it does that. Okay, now this is probably going to get itself all choked up, right?
Yeah.
Okay, but although that could be supported.
Yeah, I mean, we have the same problem that the fundamental output structure that series uses is too limited.
No, this is not, we're not going to do this. We're not going to have another one of these. We put in something new and then we can't explain to anybody why they should use the new thing versus the old thing.
As I said, the killer application is that it's not the expression case, even though the vendor will argue up and down that it's much cleaner output than series and all of that. I think that the killer use case are the combinations of solvers in active terms.
Okay, well, that's a different use, but which could perfectly well be supported in series. So let me understand something else. In series, we have this nice plus order whatever, and series automatically, if I take that series %3 and I take it to the 5th power, it will do the that meant %3 to the 5th power. It will do the right thing, right? What's the analog of that? Is Devendra here? Devendra?
I'm here. Yes.
Yes. Okay. So what's the analog of that for asymptotic series?
There isn't, because that relies on the series data structure to do that.
I understand that, but so what I'm saying is, I think that's a good feature, and you're blowing that feature up. So if I do it with something like a Laplace transform,
that only works. That only works for the class of power-oriented series.
It's very, very tiny.
Why? Because because the closure operations are not there for general asymptotic series.
Yes, okay. It's a much wider class, Stephen. I mean,
I'm not buying. Okay. So give me some examples.
Right. So you take an asymptotic of let's say, okay, so asymptotic inverse Laplace transform. How do you do that without having a much more general kind of object?
I don't buy it. I don't buy that. I'm sorry, I just don't buy that. I mean, look at this case. Okay, so this case, let's take a look at that case with a series. Can we do a series expansion around infinity?
Yes, you can.
Okay, so let's take a look at what this is doing relative to that. Okay.
You only have one term actually over there. So now it only has a leading term. So.
What do you mean it only has a leading term?
Well, the point is that we may not know the other terms in the series. You just have a leading asymptotic, which works. Now, we could probably give a message to that effect, but...
I'm sorry, what are you talking about? Okay, there are results.
You specified second order, Devendra.
Yes.
You specified beyond leading term.
Yeah, so if you did order 1, you should get back what you want.
No, I'm not. No, I want to know, why is this not expanding it in successive terms?
Right.
Why did it stop?
Because we only have...
No, first of all, it can't. I mean, so, Stephen, that's what I'm saying. There's different orders of growth. See, yeah, that can't be expanded in the full, in X powers. Can't express e to the I can't even read it. Minus e to the minus
fair enough.
Squared. Okay.
Okay.
And it's the same. It can grow too slow for a power kind of series. If you have nested logs, it's too slow for power-oriented series.
I understand all of that. Okay, so, but I'm not getting. Okay, so, this order concept, I thought also worked for. I mean, it's not obvious to me why that doesn't work perfectly well by saying order e to the 1 over x or something instead of just order x squared or whatever.
Because there's so many scales available to you. Which one are you going to pick?
Which scale are you going to pick?
There are just lots of them in the continuous and discrete world, and series captures a few of them really well, but can't go beyond that without a lot of further work. And we
can't have the user specify the scale. Okay, yeah. That would be a success rate that's probably approaching 0.
Yeah. Sorry. Say that again.
Okay, an asymptotic series is unique if given the scale. However, as a practical function, you won't know what scale you need to use to express the solution in until you know the solution.
Yeah, I understand. The scale as in...
So if we delegate back to the user to specify the scale,
no, it's hopeless.
I think that the success rate is going to be close to zero.
Hopeless. Okay, what I'm complaining about, okay, look, here's the fundamental problem. What you seem to be doing is rewriting series to be better, okay? Except that you're dropping certain features. And that, I'm not buying that.
So fine, you're not buying that. Because you want this auto-evaluation of series. And I'm saying that we can do a bigger study, and I can demonstrate more clearly why it can't be done.
Okay, fine.
It can be a lightweight version, but it cannot in general support the set of closure operations that you can do for a power series.
Okay, so let's take a look. Let's take a look at something like asymptotic solve. Okay, so asymptotic solve has features, I assume, that are, oh, for goodness sake, that I assume that it's just simply inaccessible to anything to do with series. Is that a true statement, or could one imagine? So asymptotic solve.
First of all, it needs a sort of an interface that's specified, right? That says, you know, how do you get the input data? There should be solve-like interface, first of all, right? But you could have an unevaluated or an inactive asymptotic. I mean, you could have an inactive solve or something like that, and in the principle probably specified it. I mean, that's what I mean by you have an inactive integrate.
Okay. Look, for 30 years, we've given people the opportunity to think of power series and to manipulate power series in the same kind of way that they manipulate things.
They can still manipulate power series that way. They just can't manipulate general asymptotic series.
I understand that. I understand that. I'm walking through this. I don't think it's a, okay, hold on. Okay. We give them an expectation that there's this thing that, okay, I want to walk through it a little bit more slowly. Okay. Okay. So, you know, we've got a nice analogy going between number precision and what happens in, in series. Okay. Now, the fact is, if you say, what is the limit of something, you know, all bets are off. You just got the limit. If you say even what is such and such an integral, what is the asymptotic value of such and such an integral, not the expansion, but just the asymptotic, well, I guess it's a different, I guess that's just a limit. I mean, in a sense, I'm just trying to understand, you know, because what you're delivering here, asymptotic in this case looks like a limit. What's the difference between this and the limit of this thing? I see, because the limit is not parameterized by x, right?
Well, I mean, the limit of something, if you have an asymptotic series, is the same as, first of all, if there is an asymptotic series where the first term is a constant, that is the limit, period.
Yeah, I understand. But in this case here, where you've got a more complicated scale, you do have a limit because e to the 0 effectively.
Yeah.
But what asymptotic is doing is it's giving you the expression. Okay, I'm just, let me, I'm a little slow here. Okay, so in the case of a series, you are defining something which has some radius of convergence or whatever else, and it is essentially an approximation to a function.
Right.
Yes.
And that approximation, there's a degree of approximation that is known, and one is able to, when one does operations on that, one can, you know, get the thing to the right level, so to speak. Just 1 second here.
Now, there is a candidate output wrapper that I would like to do, but we didn't have time to prototype and get it up and running sufficiently, which is much less ambitious than what series data does, which only applies for a very important, but still a tiny set of asymptotic scales, which is to maintain the partial order, because these terms are always ordered correctly in the scale given. And then one could typeset it more nicely. The downside is that you can't immediately evaluate it to have something happen. You need to do normal or something like that. But it would typeset nicely.
Well, what do we think is good? I mean, in the case of a series, sometimes it's annoying. You just want to. I mean, the problem is, do you numerical value of a series? I don't even know what happens if you do that. I think it works, right? I mean, if I say series sine x 0 10 or something, and then I say %/.x arrow pi over 10 or something. Huh. That's an interesting problem. Okay, so I have to do normal before I do that. I mean, we probably could make this work.
Yes.
Okay. So all right, I'm still trying to understand this. So, I mean, there's a trade-off, right? So what do you typically do with the asymptotic output, like e to the 1 over x here? What would you typically do next to it?
So, well, I mean, sometimes asymptotic is used for understanding. If you're going to say that this algorithm is of this growth, for instance.
Yeah, I get it, right. But so it's a terminal thing in that case. But I'm asking.
It's a terminal. It's not always a terminal thing. It's also an approximation. The asymptotics is used as an approximation.
I understand.
In which case, you're going to numerically evaluate it a lot, probably, and use it in place.
But so in the case of series, it's not uncommon to do serious operations on the series. Like you want to do, you're trying to do series solution of an equation. You want to, put in a series expansion for some variable and then let it propagate, right? The propagation is important, just like it is for numerical evaluation. But you're telling me that for asymptotic evaluation, propagation is not so important because it's not achievable for some reason.
I mean, it's not possible. I mean, you can't. This thing that works for the class of Puso series,
yeah,
just doesn't work for more general classes.
Okay, so because there isn't a hierarchy of orders in the same way, or what?
That and things like multiplication is not even defined necessarily.
Can you explain that?
No, I can't give you a super good example. I would have to drill down, but this is what happens, that you get sort of lack of closure operations.
Is this Hardy Fields business, or is this something different?
Yeah, it includes the Hardy Fields. That's one thing of it. It includes a lot more than Hardy Fields.
I see. So for example, if I do as asymptotic, let's take a very simple thing. If I say asymptotic sine x goes to infinity. I see. So if I were to say, it's just going to say this is a thing. That's the result then. And if I say comma, you're going to say that is a fundamental result, as in, yeah, I see. So now, but if I put inside there x over x minus 1, for example.
Yeah, because you're basically evaluating it at 1 for x at infinity.
Yeah, okay. So, I mean, this is a very funky creature. So you're telling me that the base expansion thingies, I mean, like for a Poiseuille series, power series, Poiseuille, whatever, the base expansionoid thing is x to the p. Where?
Yeah, actually, it's not general p. It's rational. It's n over q. I mean, it's p over q, where those are integers.
Right. Well, so there's a nice ordering of those kinds of things, right? So you're not getting into some undecidable. Is this particular transcendental expression bigger than or smaller than this one, and so on.
Right.
Okay, but in this case, what you're telling me is there are these completely non-commensurate. So this thing is a unit in some sense. In other words, that is different from this guy, for example. Right? You're telling me. No, wait a minute. That is wild. Or maybe it isn't so wild, because that's just the expansion of x minus 1. So, I mean, what you're saying is the things that should be considered as non-divisible, non-expandable bases, I don't know what they're called. I don't know what those things are called. The things that are the base of the expansion, so to speak.
Scales.
Scales, okay. So there are a bunch of, there's a whole bunch of sort of non-commensurate scales, is what you're telling me. Is that right?
I don't know if I can express if that's the correct way to say it.
Okay.
I mean, commensurate.
I don't know whether that's the right way to say it either, but
it's something has to do with rational numbers, commensurate.
No, I understand, but I mean, okay. So let's walk through what it is, the features that's asymptotic, and asymptotic value. Why did you introduce asymptotic only now? I mean, why?
Because
why
it needed. I mean, I said the killer thing. It should be able to solve all the things that if you have an unevaluated integral and an unevaluated sum, and you have them plus together, they might lead to cancellations. If you're going to get the asymptotic correct scale for the sum of them, you need individual solvers, and you need to possibly back propagate.
Okay, but so I mean, but if I had a D eigen D solve, would that also be supported here?
In principle, yes. I'm not sure. Do it now, but yes.
Okay. Okay. So I've got a couple of comments here. So first of all, is there any good reason why we shouldn't support inactive integrals and things inside series?
I think that we probably should. Not quite sure what the long-term consequences are of that.
Seems harmless. I mean, it seems like if we can do it, we might as well try to do it. I mean, and there may be plenty of things. So now the next question is, okay, so I've got two questions about this. That's one of them, is supporting unevaluated, inactive mathematical constructs and series. The other thing is when series is basically pretty useless, as in, oops, what am I typing in? Help? Did I just mess up your? Sorry, let me just erase that. When series fundamentally is going to not do much. I mean, so if I say series 1 over sine 1 over x 0 4 or something, it's going to do nothing, right? It's just going to leave it whatevered. Now, presumably, if I say asymptotic of that, it will also leave it unevaluated, but it will be prouder about it. Do you see what I'm saying?
Prouder about.
Well, as in the sense that this one series is embarrassed; it can't do anything here, right? Here, asymptotic is like, great, I'm giving you the asymptotic result. Be happy,
right?
Okay. So what I'm thinking is there may be a way to dovetail these a bit better by doing something in a case like this of like generating a message that basically says, I'm not, this isn't a fully formed thought, but as a way to kind of get series and asymptotic to not look like they're in competition. Do you see what I'm saying?
Yeah.
So, for example, generate a message saying no Poisson style series is available, giving asymptotic results or something, whatever the right thing is. You know what I'm saying? So that you're giving a clue that there's something that's more in the asymptotic, bailiwick than the series one. Does that make sense?
Right. Not quite sure, but
well, the whole point, Roger, is we can't have functions that look like they're dueling.
No, yeah.
Right. So I think what we need to do is series has been faking it for decades, pretending that it can do series expansions that it clearly can't do, like this one. Right. And like, for example, presumably if I do, let's take a look at what happens. If I do area AI around infinity, okay, now I'm just totally confused. I'm just totally confused. I mean, okay, it did an okay job with that.
Well,
and now I do asymptotic. Okay, now I am terminally confused. Okay, help me out here. Why is the ordering different?
Well, they're both kind of not ideal. Okay, so first of all, that first object you see, that has nested series data objects in it somewhere.
Yeah, that's horrifying. Right.
Okay. But where there is a series data object, the order locally within that, if you can identify where they are, the order is going to be kind of natural. Now, the one that you see from asymptotic, it relies on plus ordering, which is slightly arbitrary for other reasons. And it may be good or it may not be good.
Look, I think that even generating a message here saying no Poisson series available, no ordinary power series available, generating an asymptotic result would be a useful thing to do. And then this one.
But then it would have different output structure. It wouldn't be a series data. So then.
No, I'm saying. Well, okay, fair enough. Then I'm saying generate what it's generating now, probably. Unless you think you can improve it. I mean, see this O thing. Does this O thing? Yeah, the O thing never contains anything other than a power. Is that correct?
I think so.
So I think you guys need to explore that a bit, because I think that assume the O thing never contains anything more than a power. It does raise the question of whether it could be generalized for the O thing, although you say the math just isn't there yet to be able to do that for general, because you can't deal with these different scales and order them correctly and so on.
That's right.
Okay.
You don't have, there's too heavy. I mean, first of all, the arithmetic operations work for power series. And so does the two big things, the inverse function and function composition. Those are the heavy duty things that make.
Do they work for asymptotic series as well or not?
No, they don't generally work.
Okay, so
for scales other than that.
Okay, so let me just understand that. So in the case of, I can see that inversion might get really hairy.
Yeah, but the inversion and function composition are more or less the same.
Okay, fine. All right, so listen, this is my suggestion, okay? Let's figure out how to clip the wings of series a bit by generating some messages saying, I'm producing something, but it isn't really very useful, right? Use asymptotic if you want something useful here, to lead people towards asymptotic. Meanwhile, there is no good reason series can't deal with, within the domain of things that do have power series, deal with things like inactive integrals. And I suggest it does.
Right.
Okay. So that's my initial suggestion here. Let's take another look at this with that in mind of, how do these functions dovetail with each other? And it's perfectly reasonable for series, it's just like, okay, you've got, certain linear problems that have, endlessly more capability than the nonlinear case, right? I mean, like, root objects can do a lot more than some bizarre transcendental root can do. That's a bad example. But, I don't know, let's say rational numbers. We can clearly do more with rational numbers than we can with arbitrarily complicated root objects. So similarly here, it's perfectly reasonable to provide people with a series that in the domain where you can use power series, which is all kinds of plenty of things in engineering and elsewhere, it'll sing and dance and do lots of great things.
Sure.
But we need to make sure that whatever it can do, whatever, like Laplace transform, there's no reason a series can't deal with an inactive Laplace transform, unless the Laplace transform doesn't, come out in terms of a series. But now it's perfectly reasonable to say, okay, there's a larger class of higher wire act things, which are the asymptotic series, asymptotic expansions, And
I mean, to be clear, what
series
series develops is also an asymptotic series. It's just that the class of such things is richer. We needed to just express.
Well, it's not really an asymptotic series. It's a.
Yes, it is.
In what sense? You mean? In what sense is it an asymptotic series?
It is any power scale, near wherever the point it is, it's asymptotic.
Okay, fair enough. In that sense, but yeah, it's also a special thing, just like a linear problem. It's a special thing.
That's true.
It's a power series, and we've got a lot of apparatus for dealing with power series, which cannot be generalized to arbitrary asymptotic series.
That's right.
And some other things that can be. So there's nothing wrong with that. That's not embarrassing. No functions have to duke it out in a dual, etc. Right? So with that in mind, let's take a look at what you have here. Okay, so I'm going to make a bunch of suggestions here. Okay, so first of all, let's figure out how to make series generate a message in these cases. Second of all, let's make sure asymptotic can deal with unevaluated inactive functions. Also, this syntax of x goes to x0, I kind of think we should support that in series also. Now you've got a thing here that says asymptotic terms.
Yeah, that controls the number of terms from
I know what it controls. I can see that. Yeah. Right, it's equivalent to having.
Yes.
I'm not sure I'm that keen on that name.
I see.
Is there an analog of that name elsewhere?
N some terms.
That's not its happiest. That's not that was a kind of a hacky option.
Yeah, I'm not saying that's a good name. We could change that for sure.
Okay, the point here I'm thinking is if we could get a name here that could be reused in series, then we could support the x arrow 0, which I would like anyway, because I think it's it goes with limit much better.
That's the idea.
Exactly. So it kind of straddles the boundary between those two.
Right. But I mean, if what we could do is to say something like, look, I mean, here's what I would say. I mean, I would call it like expansion terms, expansion order. Is expansion order right or expansion terms?
This is a problem. When you're in the class of power series, then often people want to think in terms of order.
But order doesn't really mean anything. Yeah, it doesn't really mean anything. So, I mean, if we call it expansion terms.
I don't know. We haven't gone with it. We've called it approximations. We haven't called them expansions.
Okay, well, then we shouldn't do it here. I mean, the analog of this for, it's things like precision goal and so on, right? Is the
yes.
I mean, it's a little weird and probably not good, but terms goal, because you might not even get that many terms.
That's an interesting idea, actually.
I mean, that looks like kind of more honest, if you like, in a way. We are saying that that's what you really want, but we may not be able to give it to you.
Yeah.
And that
I don't really like terms goal as such without more decoration bothers me because it's just too weird.
But it's roughly what happens in practice, that we search for them, but we may not find them.
Right. I think that's what we should go in that direction. But now, what's the right name? Do we want to call it terms? I mean, the problem is if we call it asymptotic terms goal, as you say, well, how bad would that be for series?
Would you call it series terms, or would that not be right for asymptotic then? I mean, I think series is a kind of more general term in some sense for common usage,
I don't know. Roger? I mean...
Well, it is an asymptotic series.
Yeah, so I think calling series
we don't call it that. We call it a power series typically, because that's what we do want to call it, because it's a... Now, what about, okay, so here's a question. Series, all the things like series coefficient, do those work in any way with asymptotic or not?
They work with discrete asymptotic, which is the discrete version.
Okay, well, let me take a look at that in a second.
Okay, so what that means, and this was one important case we wanted to get to, but I think you guys both talk past each other, so let me explain. Series coefficient is the same as inverse Z transform, right?
Oh, that's true. Yeah.
Okay, so it's the inverse of a generating function. Now, when you do, so one way that you can, when you analyze algorithms, for instance, you often get a generating function, and you want to get the asymptotic series coefficient, because that tells you the asymptotic complexity of the algorithm.
Mm-hmm.
That was an important case to get. So yes, you can use discrete asymptotic of a series coefficient of something that doesn't evaluate, or you have it inactive, and it will compute it using asymptotic methods.
Okay, you're showing an example here.
Yes.
That's cool.
Yes. That's from a book on generating functions by the Wilf. So it's a standard thing which we couldn't do for so long, and now we can. Visually solve the kind of stuff.
Somebody at the company, a student of Wilf's. I seem to remember somebody in our orbit.
I vaguely recall that too. I can't remember who.
Yeah, I can't remember who it is. Okay, so that is, and so now if I were to say series of series coefficient,
there's no discrete support basically over there. It's a discrete variable.
Yeah, it doesn't understand discrete variables either.
I see.
So we do need a discrete asymptotic for sure, because it's really...
Wait. Before you guys jump. Okay. You're saying that
so for instance,
series,
discrete asymptotic of prime of k, as k goes to infinity, will give you something.
With that particular example right now, okay, sorry about that. I don't know what happened, but in the last few days, there was some issue with it, so I can look at it.
Okay.
I don't know what happened, but something changed somehow. I need to look at it.
Okay, but this should give you...
You can do partitions P if you like. Sorry about that. I apologize. It is something happened, and it's not in my control, really.
That's very cool. Let me just understand this for a second, what I'm seeing here. This is very, very cool.
Yeah,
very
so
impressive.
We're starting to get a lot of asymptotics for our discrete sequences, number theory.
Yeah, that's extremely impressive and interesting.
So we've done a survey of all of them and trying to get the whole lot with Charles's help, because I'm not really an expert in this area. No, that one probably will not get you very far, because it's going to try other method, but we only have the leading term over there.
Wait. I mean, we only have the leading term?
Because it's only,
that's why I've been insisting to get those, knowing how much we have and how far.
Yeah, I'm pretty sure over here that's correct.
Well, I'm sure it's correct too, but I'm annoyed that I didn't get that report back on.
Okay. So, hold on. Okay. Magnificent. So I mean, like, for example, if I do %34/n goes to, I don't know, 200 or something.
Yeah, and then you can do an n of that, and that you might need to go to high position over there.
Well, I don't think so. So now I say partitions P
200 and then n of that.
Yeah. I know.
Sorry.
It's okay.
And it's so often that.
Very cool. Ramanujan would be proud, no doubt. Okay, I understand. So let me just try and ingest what you're telling me here. So in a series, the variable might be like close to 0, for example. And then it better be a continuous variable, so to speak, a real variable. At infinity, it could either be a variable that's going to infinity like a real number, or it could be going there sort of in steps as an integer.
Exactly.
Okay, so in principle, series could take, in the case where you're expanding about infinity, it could, in principle, I'm not suggesting it does, because I suspect that the mathematics is totally different, take essentially a domain. In other words, what we're saying here, so asymptotic, so discrete asymptotic is analogous to,
discrete limit.
Discrete limit.
Yes. So, I mean, in this case here, so if I were to say for this one, I put it in the wrong thing here. But if I were to say for this one.
Yeah.
So the thing is that if a limit exists for a continuous thing, it exists for the discrete thing. But it can exist for the discrete thing without it existing for the continuous thing.
Sorry, it can exist. Yes, absolutely. Right, I understand. Now, why didn't that work? Because that's n goes to infinity. That should just be 0, right?
Yes.
Uh,
Why didn't that work?
I'm not sure. I could look into that. But, I mean, we do try and support these operators at discrete limit, but I don't know about this particular one. I can check.
Yeah, okay, fine. All right, so now series coefficient also works when applied to a series output, right?
Yes. If it's within the, the
Radius of conversion.
there. I mean, if it's because the series, when you get series data output, it's finite. It's like a finite list, right? So it needs to.
Okay, so this documentation is complete nonsense. I mean, that first thing, I suppose, is correct.
I think they're all correct.
It's a bit misleading. We should probably move that one down to the end or something, because the other is a much more. So, I mean, this does two things then.
Yes.
Because it. So here, I can just say n is 8, for example.
Yeah.
Yeah. Only the odd ones.
Okay. Okay. Which is then equivalent to series coefficient of sine x. That's very weird. x09. So it's the terminal object. In other words, this is okay.
Yeah.
So it's the series of order n. But now this series coefficient in here, this cannot be an asymptotic thing. This has to be a power series for this to make any sense. Right?
Yes. That's how series coefficient is defined.
Right. Because otherwise there's no way you could ask for the nth one.
Right. It implicitly assumes a power series.
Yeah.
Absolutely.
Okay, I'm getting this. I mean, this is pretty reasonable. I mean, we can explain this. These functions don't have to be embarrassed about each other. It makes sense.
I don't think that they are. I mean, I don't.
No, I understand that, but we have to do things like, as I said for the fourth time here, making sure that inactive of integrate works in series and so on.
Yes, I made a note of that.
Okay, all right, fine. So discrete asymptotic. It's a bit of a weird word. I'm a little concerned about the term asymptotic.
I mean, it could be asymptotics.
Asymptotics would be good too. I mean, that we're fine with that.
But this is wrong. That first usage methods is wrong. It isn't a series approximation. It's just an asymptotic approximation for x bar at x goes to x0.
That's true. You could skip the series bit.
We could skip the series. We didn't know exactly how to put that, so we agree with that.
Well, okay.
Can
I change it? I mean,
yeah,
gives an asymptotic. Well, I don't know that I actually should change this. Do you want me to or not?
It's fine with me. The Roger might.
Yeah.
I think that's correct actually.
I mean, there's a more detailed explanation below in the notes.
Okay, fine. But I mean, okay, why don't I let you change it rather than me writing this file back? Okay.
Fine.
Gives an asymptotic approximation to x bar at at the point x goes to x0.
Okay.
Right. Okay. So now, and so then what we're going to do then is we're going to say series terms goal.
Just so you understand one other meta point I have here,
which
is not explicit in these notes. So we have a limit function that says limit x bar comma x goes to x0, and then there's all kinds of multivariate extensions.
Yep.
Now, we can only solve two cases, but we need a third. So we can solve the case where you approach that point from any direction in the domain. You know, if it's univariate, it's in the complex domain from any possible direction.
Yes.
Or we can approach it just along a line, a ray. That's the direction. That's the old direction thing. And it works the same way multivariate. Either we can approach it through any direction in a complex ball or a real ball, or along a line. But as you know, for special functions, what happens is that we have a well-defined limit in a sector. You know, so it's not a full ball, and it's much bigger than just a ray. And so there should be a constrained limit, effectively.
I understand. How does that relate?
So where we need a cone, you know, a typical thing, and we need a better cone language and so on. You know, sector and cone language.
Well, and there's no guarantee that the thing doesn't look like a potato or something, the region of where something is true.
Well, that's true. But, you know, the question is, should we be able to give that in? And right now, there's a particular hang-up with assumptions can't apply to variables, only to parameters. And maybe we can overcome that in case we have something good.
Okay, but let's review the bigger class of things. So another one is contour integrals, where you have to specify the contour.
Well, that's a complicated thing for other reasons. And we are working on that now for an internal project, but it's still very far from a user-specified language, because what people don't usually want is to specify the detailed parameterized contour, and we wouldn't want them to anyway, because that's not very usable in practice, except for
right. But I mean, there are named contours, like, I don't know, the Bromwich contour or something.
That's true. There's a bunch of named things. But the typical thing you want to do is to include things or exclude things. You know, exclude this pole or this singularity. Exclude this branch cut. Include this singularity. Do you know what I'm saying?
I see. Yes.
So so to get the right level of symbolic description that's actually going to be productive, there's a little bit of work.
No, I like that. I mean, that sort of set theoretic kind of version of include, exclude, and so on.
Right.
Seems useful. And, you know, because it also doesn't matter, you know, if certain features of the function are, I mean, you know, by Cauchy's theorem, among other things, right? I mean, it doesn't matter where you are. So it only matters if you have these features of the function in or out.
Exactly. So that's the more the essence of what people are trying to use contour integration for.
It's a really good point. I mean, it's almost like the exclusions business in ordinary and integrate, right? We have an exclusions. We certainly have that in
yes.
Right. And so, in a sense, this is some kind of bizarre, complex analog of that story. Is that a true statement?
Yeah, it's a very similar, but it needs to be worked through in detail so it's operationally effective. Both can be implemented and effective from a user perspective.
Yeah, I mean, also there are going to be named things like saying, you know, ignore, you know, go outside all the poles of this function, even if you don't yet know what the poles are.
Yeah, things like that. That's the more kind of a language I think is needed for productive. Then if you do specify, today you can specify the detailed contour. And by the way, if you specified a contour for a symbolic integrate today, it will actually, as of 12.1, start using internal contour integration, because we understand all the singularities of the X-burst.
What do you mean you specify the contour? With a parameterized thing in the complex plane, or what?
Yeah, so it can only deal with, you know, if you, in the X goes from X min to X max, that can be a list of points. So it's basically a polygonal path.
Yes.
Okay. So it's just unless you give a parameterization, in which case it looks like an ordinary integral, it's just a polygonal contour path that we can support today. But if you do that, it will actually try to use Cauchy's theorem, because we have very efficient ways to get to all the singularities. And for
so if I have a real integral, you know, integral from minus infinity to infinity, I could say minus infinity I infinity. Is that right?
Well, I don't. But you could try it, but I don't know. It's usually something special with infinities. That's
okay. But I mean, if I say something like, what's a good example? Like a Hilbert transformy type thing, Well, I don't really know if this
Yeah,
but minus infinity, I infinity.
that's not a closed contour there, first of all. It needs to be closed for Cauchy's theorem to apply.
I understand. Okay. So then I would go, so that will look very weird in here because it will be something which appears to be going back to nothing.
Yeah, I mean, God knows what exceptions there are for infinities.
Okay.
You know, in how Adam has implemented this right now. I mean, there are impressive cases that do work, and as I said, the future of those such a function is more elaborate.
Oh, look at that!
Yeah,
what
that's
do you
the
know?
case.
That's pretty cool.
I think
that's never
probably
worked before, right?
I'm not sure. I think it might have worked actually.
Huh.
But there are other impressive cases. I can't find one right away unless I go and look at.
Right. Okay. But fine. But I mean, Adam obviously has to work on the infinity case because this is. I mean, that's a pretty usable and interesting thing. Being able to do that. I mean, there are cases clearly in which it doesn't have to close the contour. You know, if the function is symmetric and things like this, in which it can do all kinds of things to essentially use Cauchy's theorem without having the contour explicitly closed.
Yeah, there are a bunch of things there. You know, an implicit close of this nature or that nature in that literature.
I understand. Okay, let's come back to asymptotics. Okay. The word asymptotic and discrete asymptotic. So you're saying discrete asymptotic is reminiscent of other, you know, discrete something or other function.
Well, since we can't say sequence, we've been forbidden to say sequence for sequences. So we call them discrete functions. You have forbidden us.
Well, because we're using the sequence for something else.
Well, it just means a list without list header. I mean, it's something in the low-level language.
No, Roger.
So we have to use sequences.
No. There are things like sequence position and so on, which is something completely different.
Right. But anyways, in the mathematical part of the system, we don't call sequences.
Yeah.
Because we can't.
Okay.
According to that design rule. So.
The thing that bothers me is the term asymptotic is sort of the wrong part of speech. It's an adjective.
And the only thing that drove us is that asymptotic of integrate should give you asymptotic integrate, which may not be a good reason from your point of view, you know. So asymptotics is fine too if you think that's better.
No, asymptotics plural is awful. That suggests that you're going to get a report.
Exactly. Yeah.
Okay. So an asymptotic series would make sense if it wasn't for the fact that you have a common case, which is the one-term case.
Yeah.
All right, asymptotic can be, and so the description of discrete asymptotic is it's an asymptotic approximation to the discrete. What is the description here? I just don't like discrete asymptotic very much as a. What are you doing? Why are you writing it with an explicit infinity here? Why are you not writing it with an x0?
Well, I mean, the only interesting place for a sequence is infinity. Finite point.
Well, why then are we not just allowing it to be x per comma n? What about minus infinity?
Yeah, minus infinity should work too.
We could do that, yeah.
But it's stupid. I mean, come on. The syntax where you say n arrow infinity and the arrow infinity doesn't matter is clearly wrong, right? Okay, so what we need to do here, could you possibly stop grinding a piece of paper on your desk or whatever you're doing there? Okay. this doesn't make sense, right? I mean, so if I say n arrow 10,
and you can only approach it over the integers.
Yeah, it's pretty stupid, I agree. So an n arrow 0 is not interesting. I mean, basically, for the case of ordinary asymptotic, 0 and infinity are both interesting. And 1 is interesting too, if you've got a bunch of x minus 1 terms.
No, any point is interesting for ordinary. Over a continuous domain, any point is interesting.
Okay, so what are the other things that, like discrete limit? Does it have the same issue of only infinity is interesting?
Yes, or minus infinity.
Okay, so I strongly think we should support discrete limit f of k. What the hell is the f of k doing here? We don't do it that way. We don't write it like that. We write it as expo, right?
Fine.
Because it isn't always an f of k. I mean, we could have written it that way, but we don't, right? As in this example shows. But I don't see why you shouldn't then support discrete limit expo comma k with the arrow infinity elided. See what I'm saying?
But not documented.
No, I would document that. I don't see why you wouldn't document it. Gives the limit as it goes to infinity, because that's what you want. That's what, when you're talking about discrete limits, that is what you want. That is the story, that it's going to infinity, right?
Yeah, or minus infinity.
I know, but you can, if you really want minus infinity, you can say n arrow minus infinity. But if you just say comma n, let it be defaulting to infinity.
Sure.
And similarly here, I would give a 2-argument form of that list, n comma m. And I don't know why it's called m, because that's like super confusing. I mean, you should call this is really a mess. Come on, using k here, use k here, use n for the order as you have in the other things, okay? Make sense, Devendra? Hello, Devendra.
Yes.
Okay.
Actually, I see another problem here, but it's futurized. It's just too many uses of n. The n variable case uses n variables.
Oh,
just like can't have that. It's okay.
In this case,
it's futurized. It's not now. It's future.
Yeah, right. Yes, I'm sure that was done differently in the series case. Okay, notwithstanding all these design comments, but that's what these meetings are for. This functionality looks absolutely fantastic.
Thank you.
I do want to see, so a bunch of famous theorems like the prime number theorem presumably are represented in this functionality.
Yes, it is.
Yes. You can do asymptotic of prime pi of x and you should get back the asymptotic over there. And there you get the full series actually. I hope it's still working. There's some issue with prime prime pi of x, I guess you want, yeah.
Of x, yeah.
Yeah, that's okay. It doesn't matter very much.
I wish it didn't reorder it like that. That's kind of a mess that it reorders.
That's what I'm saying, that if we had a different output wrapper that had maintained a partial order, then we can both typeset it better and it would not.
Yeah, on the other hand, the disadvantage of that is then you've got the annoying thing of having to do normal all the time.
Exactly. That's why we haven't done it. But the typesetting of plus and times is getting really annoying.
I agree with you. Look, I suspect what we should do, I mean, there's all kinds of stupid things, like the constants of integration being wrong, et cetera, et cetera, et cetera. The question really is, to what extent can we imagine breaking away from what you see as the ordering you have? See what I'm saying? If we could break away from that, we could imagine storing internally information about what the ordering is, some advisory information about the ordering. I'm not sure how.
So I don't know if I should say this here, but I think that, I want to launch a pretty serious initiative to make formulas insightful. I think that there was a time when people were very proud of giving something that has multi-page output, but has zero insights in it, because you could. But I think that that's pointless. We need to have formatting that takes advantage of. We have the most serious formatting system in the business, and we can actually create insightful formulas. So that means that it's going to do a lot more work on typesetting going forward.
Well, and I mean, look, the thing we've been working on independently is things like the code folding, formula folding type stuff.
Sure.
Of eliding pieces and so on. Which
right, but this is the analog thing for mathematical formulas. If they're going to survive and have any meaning going forward, they have to be insightful. If it's going to be machine code, who the fuck cares?
Yeah, but I mean, I think the question, there's a different point of view. Insofar as publications start to be interactive, then you can do very different things with formulas.
Yeah, but that doesn't that doesn't change anything of what I said. You can, but
no, but I understand. But that's a driver.
Actual publications do exactly what I described. They do create insightful formulas. They do not publish machine code. They put effort into making them insightful. So there, it's very well developed.
Okay, but I still think, well, okay, separate topic. The plus ordering discussion is one that we probably should continue. I pushed it again a couple of times with multivariate ordering and changing that and things, and I think we should continue that discussion because I don't think it's optimal. I think we can have some. Yeah, can we put that, please? I guess Devin is the one taking notes and so on here.
Yep.
I mean, it's not for tomorrow, but it's a discussion I want to try having again. I mean, I've tried having it a couple of times. Each time, typically, Itai convinces me that it's impossible to do anything, but I'm not. Okay. I'm not firmly convinced. Let's go through. We're not going to agree on the experimentalizing right this moment, but I expect we can. Let me just take a look at what you have here. So the forms of these solutions are still staying the same. It's merely that we have a lot more stuff that we're doing. Is that correct?
Well, forms might be changes. I mean, absolutely, forms might change over time. As we get better solvers, higher quality forms, absolutely, it will change. We're not encasing given solutions in stone. We cannot. And
I
ever agree to that SLA.
Right. I understand that point. My issue is, what is this showing? This is showing.
So this is a benchmark that has 1461 PDEs. And now you see SymPy and Maple and Sage doesn't have any PDE support.
Right.
Okay. And you see us 11.3, 12.0, 12.1.
Okay, that's good. Okay. Well, but there's still 29% that we can't do.
That's right.
Yes, and that's quite a large number. We have a notebook with all those. We are trying our best on all Goktas, actually.
And what, I mean, for integrals, the number that we can't do is vastly, vastly smaller than that now.
No. Let's do that in another. I don't want to do it in a public forum. I mean, I can, but that's a big discussion topic.
Okay. All right. Oh my gosh, new basic examples. Wow. Really?
Yes.
What was wrong with what we had before?
They didn't exist uniformly. There were many missing. So now we have a kind of uniform pattern, which, no, you need to go to Bessel New, sorry, because it's still not showing up in the builds for some reason. So
most of what they've done is to include, I mean, so first of all, it's a fairly uniform template, numerical evaluation, real plot, complex plot, and some asymptotics. And then much more detailed handbook style things under scope.
Well, that's reasonable enough.
Yes, yeah, so and we have complex plots. We just want to use it and let people know that we've got this new one.
I mean, the point of a plot is to understand the overall behavior of a function. That's the insight you want to create in users' minds. And in some ways, asymptotics also creates an overall understanding of the behavior of a function.
Okay, this is not acceptable. That stuff, get rid of that shit. Don't put that in our examples. It's just completely stupid, unnecessary.
Yeah.
Okay. I mean, if you need to do this, right? No. What are you trying to show here?
Just the point, but I think it gets iconized in the actual documentation.
Why? It's not getting iconized. That's code. It'll be right there. Please don't put stuff like that in. It's completely unnecessary. It's like showing some.
Okay.
You know, I mean, first of all, these scope examples, they have not.
What the hell is this? No, get rid of it. Plot legend arrow expressions. Come on, you don't need all of that stuff. And also, please don't use @sign.
Okay.
Stephen, this was released in 12. The scope examples.
Okay, well, they should be fixed.
Okay.
I mean, you can probably deal with them. Boy, I really don't like this. I don't like having to define variables here. A lot of this stuff should probably be iconized.
It probably is in the actual documentation. You're looking at the old page. I think it should be done there. So I only got the approval for the basic examples a few days ago, so we're just putting them in. But scope has been there.
Wait. Are you saying it was in 12.0 or not?
It is in 12.
The scope, not the basic. Do you understand different sections we have in examples?
Okay, so that's not iconized. That's no. It's a piece of crap.
Right, but
let's get rid of it.
Okay, fine.
And I don't understand this. This is so stupid to do this way. So stupid to do something where you've got things going across multiple lines. You don't need to do it. It's just going to make it so that when somebody copy pastes this example, it won't work. Right?
Right.
Do we really need that? I mean, do we really need to have something where... Okay, separate discussion. Please don't put stuff like this in the examples.
Okay.
The examples are nice and clean. Leave them nice and clean. Don't have things where, unless you want to invent a mechanism, which you can certainly try and get the documentation team to do, where if you copy that line, you get that line as well. But we're not going to be able to do that in standard documentation because we're trying to
that's just because the copy thing for the web, you're complaining now. But example group is an example group. You evaluate the example group, you change whatever you want, it works fine. It just hasn't been made to work on the web yet.
Well, that's an important case. But I mean, look, just make this look nicer. I mean, in I don't know. I mean, like point size large. Do we really need that? Do we really need that? And what about the fact that you're supposed to use style wrappers, not these naked primitives anymore? Do you know what I'm saying?
Yes.
Okay. Why are we writing bad code and putting it in our examples? That's not useful. And look at all this junk.
Yeah.
Why isn't this a solve value? Why is this a /dot part 1? What is all this nonsense? I thought we had. Don't we have this thing solve value?
No, we don't. Not yet. No.
Well, why not? I mean, we need that.
Because we don't.
Yeah, but
that's why we don't have it. Because we don't.
Okay, but we should have it because that's what you.
But we won't.
We agree with that. I mean, it's just
we won't have for 12.1 because it just came up.
Yeah.
Okay, all right, fine.
I made a note of those. No problem.
Okay, but then this, please do not use deprecated forms of the syntax. Okay,
sure.
It should be this point. If you're really going to do it, if you really insist on having a red point there and you can't get it to be red by default, then do that, please.
Sure. Okay.
Oh, this is cool. Hopefully lots of people are successfully finishing the course, are they?
Well, that's not clear. We've got lots of people who actually seem to have done the work but not
We need
applied.
to have better analytics from our education initiative. I don't, the analytics we get is what they can get from Google, and that just doesn't tell us anything about how students are transitioning through the course. That just
are you using the cloud? I mean, this course uses the cloud, right?
It uses whatever we have for Wolfram U. Yes, it uses the cloud or whatever.
No, but I mean, when people answer exercises, they're doing it in the cloud. Is that correct?
Yes,
whatever
that's correct.
we use for Wolfram U.
No, I understand, but I mean, they're typing code. Yes.
They're just doing multiple choice most of the time right now.
Okay. Why aren't we doing actual type and answer?
Because I didn't even know it would be so successful. So now I've got someone who'll start off in probably January. He may be available for us. But we didn't have a clue that it would go so well, basically, honestly. So we now think that it's worth our while to do it.
Oh, yeah, fair enough.
I mean, your EIWL is a fantastic course in that sense. It's got nice exercise and all that. We aren't there yet.
Right. I mean, it wasn't exactly hard to make the exercises for EIWL. The scoring was hard, but the exercises were not hard.
Right, but we do. Sorry.
Yeah, you do scoring for multiple choice, which is vastly easier.
Yes, and then that keeps track of. I mean, people finish and they feel good about it,
Well, I mean, okay. So, I mean, that there's a whole initiative coming with courseware tools and so on, which hopefully you will be able to use.
Yes.
Will that improve the tools that we have for developing?
Dramatically.
So how many people are going to work on those tools? Or who's going to work on them?
Well, we have Rory and Sylvia are two people who are going to be involved. You probably don't know either of them.
Right.
I think that the real issue is how much heavy lifting coding is going to be involved versus how much basically just restructuring. I mean, we've got both Kyle Keen's stuff, and we've got he's developed a lot of stuff that's in connection with this, with the what he's put out from MIT, and also the CBM people have produced a lot of stuff, and both of those are sources, and we'll be using those. And it's unclear how much it's final assembly versus how much it's heavy lifting. Hopefully that will be found fairly soon.
Yeah.
And I mean, the basic strategies for how we present things using form notebooks and so on, I think will work nicely.
I mean, look, improvement on that side, both that makes it more efficient to produce courses and makes for a richer student experience are valuable.
Yeah, well, I think that.
And also, the other thing is, I said, I really want better analytics. If we're going to invest more resources into it, it's very important that we find out back, or we have to kind of stop investing in it.
Right. Hey, listen, I need to go just for a few minutes to some other meeting, and I know we have a meeting about graph theory and number theory in a moment. Let me just take 5 minutes to go deal with something else, and then I will be back, and we can work on graph theory and number theory.
Okay.
Okay, but this is not. We should probably we got to take a little bit more time and look through a few more of these things.
What does that mean? Another meeting?
I think so, yeah. Unfortunately.
Okay, so I'm flying out Friday, just so you know, and then I'm going to be back 2 weeks later.
So why don't we do this at a time when you can do it from Sweden?
I can do that probably a week and a half in, but not the first week.
Okay. Well, whatever. I mean, that it is what it is. I mean, I think we've gotten a good distance here. Most likely, I mean, we could probably combine the final review of this with some other things and fit them all in an hour.
Mm-hmm.
Okay.
Okay.
But solve value is the thing you're going to work on, right?
D-solve value exists.
No, I understand.
Solve value is not in this review.
I understand that.
Yes.
Okay. All right. Sounds good. Okay. I will see you, and to folks on our live stream, we will be back for another episode in just moments. Graphs and networks. Okay. And good work, Devendra. Talk to you all soon.
Thank you.
Okay. Bye.